Okay, just I'm sharing my screen. Okay, yes. So today we'll see discuss about the MOSFET characteristics. How the MOSFET characteristics will be there. Okay. Mm, so yeah, MOSFET characteristics. MOSFET characteristics. Okay, MOSFET characteristics. So if you see the MOSFET characteristics, so that means first we'll discuss the drain characteristics. Okay, drain characteristics. So drain characteristics, how you will draw. So drain characteristics you will draw with respect to what output voltage, that is VDS versus ID. Output current. Okay, output voltage versus output current is nothing but drain characteristics. Okay, so if you draw the MOSFET drain characteristics, so how it will look like means here, so y-axis I'm drawing, this is output output current. Okay, this is my output current. Okay, x-axis is in output voltage. Okay, so this is output voltage, so this is VDS. Okay, and this one is ID. Okay, output current ID. So here how the curve will look like, so that means here first so you have like regions we already seen. First what is this cutoff region? Okay, cutoff region, and next you have linear region, and non-linear region, and next you have saturation region. Saturation region means that the current becomes constant and the channel will be moved to from where to where, drain to source, and that is nothing but we call as punch through and reach through, that we seen in the last class. Okay, saturation region. Okay, so that means here so the curve will look like this. The curve will look like this. Okay, so this curve will look like this. Okay, so from that means here if you see, so this is 0. Okay, so till here, let us take till here. Okay, till here, so this is nothing but linear region. Okay, almost a straight line with slope proportional to v over v. Okay, so this is always straight line. Okay, straight line, and whatever the slope is there, so that slope is proportional to VOV. VOV is nothing but overdrive voltage. Okay, overdrive voltage from here to here, that is straight line. And after that what happens is that channel will be means in this linear region, channel will be uniform. Okay, channel will be uniform. And after that what happens, channel, so gradually if you are increasing VDS more and more, so what happens, the channel depth will decrease. Okay, so channel depth will decrease, and the drain current will increase, the rate at which the drain current will decrease. Okay, it is converting from what linear to non-linear. Okay, this is nothing but non-linear region. Okay, so this is nothing but we can say that the curve bends because channel resistance increases with VDS. Okay, so the curve, so the whatever the curve is there, curve bends. Why curve bends? Because the channel, whatever the channel resistance is there. Okay, so channel resistance increases, increases with VDS. Okay, channel, so that is increases with VDS. Okay, so from here to here, let us take this one. Okay, so this one, so both linear region and non-linear region we call as triode region. Okay, so what is the condition? We seen the condition also. So that is VGS should be less than or equal to VDS should be less than or equal to VGS minus VT. Okay, VGS minus VT. Okay, so we already seen all the conditions. So that means cutoff region is nothing but VGS equal to VSB equal to VDS equal to 0. Okay, this is nothing but cutoff region. And next, linear region. Okay, these conditions you need to remember. Okay, so VGS should be what, greater than VT, and VDS you are giving smaller value, and VDS is less than VGS minus VT. Okay, this is cutoff region and this is linear region. Okay, and next non-linear region. So non-linear region, if you see, so VGS is greater than VT, channel formation, and VDS you are increasing more and more. Okay, so you are increasing more and more such a way that VDS is less than VGS minus VT. Okay, so that means channel resistance will increase as you increase more and more VDS. Okay, at one point what happens at that point? What is that point? VDS equal to what? VGS minus VT. Channel will be pinched off. Okay, channel will be pinched off. Okay, so that condition is nothing but we can call as VDS sat. VDS sat. Okay, VDS sat equal to what? VGS minus VT. Okay, this is nothing but what? Overdrive voltage. VOV. VOV is nothing but overdrive voltage. Okay, and next you have the saturation region. So what is saturation region? Saturation region is so saturation region is here VGS is greater than VT and VDS is more value. You are increasing more and more VDS such a way that by pinch off condition is overcome, so that VDS is greater than or equal to what? VGS minus VT. VGS minus VT. This is nothing but saturation. So during the saturation, what happens? During the saturation, the current becomes constant. The current becomes constant. Okay. So this current becomes constant. Okay, here as so last class I told you, like so that means the channel is means the current is constant. It is nowhere depending on VDS. Okay, it is depending on VGS. Okay, the current saturates because channel is pinched off. Okay, the current, so whatever the current, so current saturates, current become constant. Okay, current saturates because channel is pinched off, because channel is pinched off. Okay, so channel is pinched off. Okay, pinched off at the drain end, pinched off at the drain end. Okay, at the drain end. Okay, at the drain end. And so as I told you, so VDS no longer affect the channel. Okay, affect the channel. So as it told, sir, that this is nowhere depending on VDS, means where it is depending means it is depending on the VGS. Okay, so this is characteristics of MOSFET. Okay, so first cutoff region means this is cutoff region only. Okay, so like if you go for this, so this is cutoff region. Cutoff region means so all, that means ID current equal to 0 only at cutoff region. Channel is not forming, that is ID current equal to what? 0. Okay, so from here you can say that VGS equal to what? VT plus VOV, threshold voltage plus overdrive voltage. Okay, so this is saturation. So we discussed about the this is linear region, and this is cutoff region, and this is non-linear region. Linear region and non-linear region we also called as triode region. Okay, so means if you observe this linear region and non-linear region, you have like VGS is less than VDS is less than VGS minus VT. So that means here so till here pinch off point, this is condition is VDS is less than or equal to VGS minus VT, that is less than or equal to VOV. VOV is nothing but overdrive voltage. Okay, and here after pinched off, the condition becomes what? In saturation, VDS is greater than or equal to VOV. So VOV is nothing but VGS minus VT. Okay, that is equal to what? VOV only, overdrive voltage. Okay, so that is nothing but overdrive voltage. Okay, so these are the characteristics of drain characteristics of what NMOS. Okay, drain characteristics of NMOS. Okay, 1 second. Yeah. So these are the drain characteristics of NMOS. Okay, so that means here if I draw the drain characteristics in detail. Okay, so drain characteristics of enhancement MOSFET in detail. So here I can draw like this. Suppose so this is ID. This is ID. Okay, and this one is VDS, okay, VDS, okay, and so that means here you are getting the characteristics like this, okay. So here if you draw the characteristics, this is so like this, okay, and here like this you are getting, okay, and next and here like this you are getting, okay. So that means here if you draw the locus, okay, if you draw the locus, this is the locus, okay, so this is the locus, okay, and so that means from here to here, from here to here, what is this region? VDS is less than or equal to VOV, okay, overdrive voltage, VGS minus VT. So this region is nothing but triode region. Triode region means what? Both linear region and non-linear region, those are nothing but triode region, okay. And after this, this is nothing but current becomes constant, and this is nothing but saturation region, saturation region, okay, saturation region. In this saturation region, the current becomes constant, so that is VDS is greater than or equal to VOV, overdrive voltage, okay. VOV equal to what? We already told this is VGS minus VT, overdrive voltage, overdrive voltage. So as I told you, so that means here let us take this is VOV1, and here this is VOV2, VOV2, and here this is VOV3, VOV3, and here this is VOV4, okay, VOV4. So as I told you, during this saturation region, so that is nowhere depending on what VDS, okay, VDS nowhere affect the drain current, okay. So which one will affect the drain current means VGS, okay, for different values of VGS. See here, VGS equal to VTN threshold voltage plus VOV1, okay, this VOV1, okay, and here also, so that is VGS equal to what? VGS equal to, you can write as VTN plus VOV2, VOV2, and here VGS equal to what? VGS equal to VTN plus VOV3, VOV3, okay, and here this is VGS, VGS equal to VOV VTN, VTN plus VOV4, okay, VOV4, okay. So this is nothing but drain characteristics, okay. These are nothing but what? Drain character. So drain characteristics are nothing but what? Drain characteristics are we are plotting the waveform with respect to output voltage and input current, okay. In the last class I told you that we don't have the input characteristics. Which characteristics we have? We have a transfer characteristics. Transfer characteristics are nothing but what? Transfer characteristics are nothing but the input voltage. What is my input voltage? VGS, okay, this is the input voltage versus output current, okay, output current, okay, output current is ID, okay, output current. So that I am going to draw here. So here what I will get, just this one you extend from the drain characteristics only, you will get the transfer characteristics, okay. So here if you see, just this is nothing but what? VGS, this is nothing but VGS, okay. So you draw here this locus, this is what? VOV1, okay, and here also this one you draw this locus, this is VOV2, and here also this you join, and here you are getting VOV3, and here if you join here, and this is VOV4, okay, VOV4. So just so connecting these points, this is nothing but we call as transfer characteristics, okay. So transfer characteristics is nothing but what? So we are plotting the input voltage VGS versus ID, okay. Drain characteristics is nothing but we are plotting the output voltage. What is the output voltage? VDS versus ID, VDS versus that is output voltage with respect to output current, Okay, this is output current. Okay, drain current is output current, and VDS is output voltage, and VGS is nothing but input voltage. Okay, so like this we need to do the drain characteristics. Hope you understood how I am drawing the drain characteristics. Okay, any doubt or any queries in this? Shall I move forward? Anyone? Hello? Yes or no, or you understood or not about this transfer characteristics, drain
No, sir.
characteristics? Okay, okay, okay. So next I will go with what transfer characteristics. So transfer characteristics means that whatever I drawn, that I will write here. So transfer characteristics. So here transfer characteristics is nothing but what here. So that means here this is my drain current ID with respect to what input voltage. So what is my input voltage? This is VGS. Input voltage is VGS. Okay, so that means if you draw the transfer characteristics, so this is 0 till here no channel is forming. If there is no channel is forming, what happens? It will be like in which region? Cutoff region. Okay, cutoff region after VGS. So that means as VGS is less than VT, there is no channel formation. So weak inversion layer is forming, but there is no moment of that, there is no channel formation. So when VGS is, we already discussed, greater than VT only, strong inversion layer will be formed and channel will be formed. So when the channel is forming, so that means it will increase like this. Again here you will get linear region, non-linear region, all those things. So let us consider from here to here this is linear region, and from here to here this is non-linear region, and from here to here this is saturation region. Okay, so like this, so that means this is so this one is nothing but what VGS is greater than or equal to VDS. This is VDS is greater than or equal to VGS minus VT. This one. So this is VDS is greater than or equal to VGS minus VT. Okay, saturation. Okay, so that means here from this I can write so ID is 0. ID equal to what? ID is 0. ID is 0 for what? For VGS is less than VT. Less than VT. Okay, so why? Because no channel is forming, weak inversion layer is forming, there is no channel, so that's why there is no drain current. Okay, ID increases with VGS. ID increases with VGS for what? For VGS greater than VT. Channel formation. Okay, channel formation. Okay, when, so that means this is what I told you, no? So this is cutoff region, so there is no drain current, ID equal to what? 0. Okay, and here you can say this is linear region and this is non-linear region, and next this one is you can consider as a saturation region. Okay, saturation region. So linear region means channel is uniform, that I already shown, and here channel is non-uniform, the rate at which drain current will decrease, and here drain current becomes constant. Okay, so here if you see what is the condition, that means when VDS, when it is coming to the saturation, VDS is greater than or equal to what? VGS minus VT. VGS minus VT. So during this, so this depends only on what? This is depends. So in the during the saturation depends only on which one? VGS. ID current, it depends only on VDS during the saturation region. We already see here. During the saturation region, for different values of VGS, you are getting the different values of ID current. Okay, so during the saturation, it is nowhere depending on VDS. So in which one it is depending? It is depending on VGS. Okay, so this is about the transfer characteristics. Okay. Okay, so transfer, hope you understood. So that means transfer characteristics is nothing but input versus output. Input voltage versus output current is nothing but transfer. So why we are not getting input characteristics means this IG equal to what? 0. Gate current is 0. Why? Because we are connecting this is MOSFET. This is my MOSFET, and this is N plus, and this is N plus, and this is P substrate. So here this I am connecting with what? SiO2 layer. silicon dioxide. This is nothing but insulator. Above this there is a polysilicon or metal, okay, and here you are giving the gate. Okay, so during means due to this insulator, that means gate current is 0. So if gate current is 0, there is no input characteristics. Which characteristics are there? Transfer characteristics. You have a transfer characteristics. Okay, so this is about the characteristics of enhancement NMOS. Okay, enhancement NMOS, and next we will see the drain current equation. Drain current equation. Drain current equation. So what is the drain current equation? So let us take first how many regions? First region. So first cutoff region. If you see the cutoff region, VGS is what? Less than VT. VGS is less than VT. VGS of less than VT means what? No channel is forming. Okay, weak inversion lane is forming, and there is no movement of charge carriers. Either it may be electrons or holes. If it is N channel electrons and P channel holes, so there is a no movement of charge carriers. IDS equal to what? 0. IDS equal to 0. Okay, and next during linear region. Linear region, VGS is what? VGS is greater than or equal to VT, and VDS is what? VDS is less than VGS minus VT. VGS minus VT. So you'll get a drain current IDS equal to mu n COX W by L into VGS. Okay, here I will write. Here place is not sufficient. Okay. Here okay. So here if you see in the linear region, IDS equal to what? Mu n COX W by L VGS minus VT into VDS minus VDS square by 2. VDS square by 2. Okay, this is the my formula, where mu n equal to what? Mu n equal to mobility of charge carriers, mobility of electrons, and COX is nothing but oxide capacitance. You have SiO2 layer, no? Oxide capacitance, that is SiO2, silicon dioxide, oxide capacitance. Okay, oxide capacitance, and next you have W by L. W by L is the aspect ratio. Okay, I think remaining you know. So that means VGS is gate to source voltage, input voltage, VT is the threshold voltage, and VDS is the VDS equal to drain to source voltage, that is output voltage. Okay, this is about the linear region, and coming to the saturation region. So what is the condition? So VGS is what? VGS is greater than or equal to VT. Okay, channel is forming, and channel is pinched off. After that, VDS should be greater than or equal to what? VGS minus VT. Okay, so here what I am doing means, so VDS equal to VGS minus VT. This expression I'm substituting in this value. Okay, I'm substituting in this value. So when you substitute, what I will get? See here, IDS equal to what? Mu n COX W by L. Here VGS minus VT into VDS equal to what? VGS minus VT minus VGS minus VT whole square divided by 2. Okay, so again I substituted. After that, if I do this, okay, so what I will get? See here. So IDS equal to what? IDS equal to mu n COX W by L. So this is VGS minus VT whole square minus VGS minus VT whole square divided by 2. Okay, so anyway LCM is 1. So IDS equal to what? IDS equal to mu n COX W by L. Okay, this is 1, no? 1 minus half is nothing but half, no? 1 minus, so 1 minus half is what? So 2 will be LCM. 2 minus 1 is what? So 2 is LCM, and 2 minus 1 is 1. So you are getting half. Okay, so this is nothing but VGS minus VT whole square divided by 2. Whole square divided by 2. Okay. So that means what is the drain current equation in saturation? I can write IDS equal to 1 by 2 mu n COX W by L VGS minus VT whole square. VGS minus VT whole square. This is the drain current equation in the saturation. Drain current equation in the saturation. Okay. So this is about the drain current in different types of regions like cutoff region, linear region, and saturation region. Okay. And next we'll see about the drain resistance. What is the drain resistance and what is this transconductance? Okay. First we'll see the drain resistance. Drain resistance. Okay. So drain resistance, if you see, so RD equal to, I can consider dou VDS by dou ID. Dou VDS by dou ID. Okay, dou VDS by dou ID. Okay. So how I am getting means, suppose you take the equation, current equation in linear region. So ID equal to what? ID equal to what you will get in the linear region. What you got in the linear region? So this is the current equation in the linear region, no? So mu n COX W by L VGS minus VT whole square into VDS into VDS square by 2. Okay. So here I am writing this equation in the linear region. In the linear region I am writing. Okay. So mu n COX W by L VGS minus VT into VDS square minus VDS square divided by 2. Okay. So we already know that is in linear region we are giving small value of VDS, no? So VDS is small value. Okay. VDS is greater than 0. Small value you are giving. Okay. So as VDS is very small value, so this is also very small value. We can neglect this. Okay. When you neglect this, what equation you are getting? ID equal to mu n COX W by L okay, W by L. So and with respect to ADS, okay, 2 you will get, okay, 2. 1 second. If you do, okay, if you do with saturation, mu n COX VGS minus, so sorry, you need to consider the equation in the saturation. Okay. For both you need to consider for the saturation only, not linear region. Okay. Suppose linear region if you consider, so linear region, here you are getting 2. Okay, how I can cancel that 2? Okay, yeah, sorry, means I need to do for linear region. Okay. So what is my drain current equation? So drain current equation, IDS equal to what? 1 by 2 into mu n COX W by L VGS minus VT. Okay, VGS minus VT. Okay. VGS minus VT means with respect to VDS if you take, okay, this is I am doing for transconductance. Okay, transconductance I will do. After that I will do the drain resistance. So VDS minus VT whole square. Okay, this I am doing for transconductance. Okay. So transconductance, what is transconductance? So transconductance is transconductance. Okay, transconductance. So here GM. Okay, GM is the transconductance. Okay, how you calculate the transconductance? GM equal to dou ID by VGS. Okay, dou ID by dou VGS. Okay, that means output current, change in output current with respect to change in the input voltage. That is nothing but transconductance. Okay, so this one is there, no? So VGS minus VT whole square is there, no? So this I am partially differentiating with respect to what? VGS, dou ID by dou VGS. Partially you are differentiating. Okay, with respect to what? VGS. With respect to VGS. Okay, so with respect to VGS if you take, so what you are getting? 1 by 2. Okay, so d by dx of what, x square is what, 2x, 2x. Okay, so that means here you are getting mu n cox w by l 2 into vgs minus vt, this two get cancelled. Okay, so that means what is gm equal to dou id by dou vgs, so dou id by dou vgs, that is equal to what, vgs minus so mu n cox w by l vgs minus vt. Okay, so you got this equation, so from this what you can say, the transconductance is directly proportional to w by l. Whatever the transconductance is there, it is directly proportional to the aspect ratio w by l. Okay, so from here I can conclude that transconductance is directly proportional to the aspect ratio w by l, width to length ratio. Okay, and next we will see the drain resistance. Okay, so drain resistance, if you see rd is nothing but what, drain resistance. Okay, so drain resistance how you will get means, so that means rd equal to what, so drain resistance rd equal to dou vds by dou id, okay. First I am writing the equation in linear region. What is the equation in linear region, tell me? So drain current id equal to what, this one, no? So drain current id equal to this one. Okay, so here id equal to what, I am writing the equation, id equal to mu n cox w by l, okay, and vgs minus vt into vds minus vds square by 2, okay. So here in this equation what I am doing means, as this is very small, I am neglecting, minus is there, so minus means it will be very small only, so I am neglecting this. Okay, after neglecting, so I am approximating the id current. Okay, if you approximate, what you are getting, mu n cox w by l, this is what, vgs minus vt into vds. Okay, this is my drain current equation after approximating. Okay, after that what you do, id, you with respect to vds you do partial differentiation. Okay, so I think you already came across partial differentiation, that whatever the variable is there, that you need to consider, remaining you need to consider as constants. Okay, so 2 or more variables are there, so with which variable you are doing the partial differentiation, that variable you need to consider as variable, remaining are as constants only. Okay, so that means here what are constants, vgs and vt, all these are constants only. So mu n cox w by l, okay, vgs minus vt into 1. Okay, into 1 means anyway, into 1 means this value only. Okay, so but I want what, I want rd, no? What is rd? Rd equal to dou vds by dou id, so this one is nothing but reciprocal, 1 by mu n cox w by l vgs minus vt. Okay, so that means from this I can say that rd, drain resistance, is directly proportional to the aspect, inversely proportional. So you got here in denominator, no? So from here I can conclude that rd is inversely proportional to the aspect ratio. Okay, so this is about today's session. So first what we have seen, we seen the basic MOSFET characteristics. Okay, different types of regions we already seen. So that is like a linear region, non-linear region, and non-linear region, saturation region. So linear region and non-linear region we call as a triode region, and the transfer characteristics and drain characteristics also we seen in detail. So we need to draw the locus, you need to take the points, and in right side you need to draw the drain characteristics, in left side you need to draw the transfer characteristics. Okay, drain characteristics are nothing but VDS with respect to ID, and transfer characteristics are nothing but VGS with respect to ID. Okay, input with versus ID is nothing but transfer characteristics. Okay, so that means in saturation it is nowhere depending on VDS, it is depending on which one means VGS. So if you increase VGS more and more with different values of V1, the ID current will increase. Okay, that we seen. And this is about the transfer characteristics also we seen. Okay, so cutoff region, linear region, and different types of region, how the curve will be there. And drain current equations also we seen. Cutoff region means anyway channel is not forming, drain current equal to 0. Okay, in linear region this is the equation. Okay, and in non-linear region, in saturation region, you need to substitute VDS equal to VGS minus VT in this equation, and if you do the simplification you will get the current equation for what in the saturation region. This is the current equation in the saturation region. Okay, so half of mu n COX W by L into VGS minus VT whole square. So this is nothing but VGS minus VT whole square. Okay, and we already seen the transconductance. Okay, so transconductance is nothing but the ratio of output current with respect to input voltage. Okay, dou ID by dou VGS. So for this you need to take the current equation for the saturation, and you need to do the partial differentiation, and you are getting this equation. From this I can conclude that GM is directly proportional to what W by L. Okay, and next we seen the drain resistance. Drain resistance is nothing but output voltage with respect to output current, dou VDS by dou ID. So here I took the current equation for the linear region. So in the linear region we are making VDS very small. So as VDS is very small, VDS square by 2, so minus is there. So I can neglect this, and I'm approximating to this value, and I'm partially differentiating. Okay, so I'll get this equation. From this I can conclude that RT is inversely proportional to W by L. Okay, so this is about this session, and next class we see about enhancement PMOS and depletion MOSFET. So enhancement PMOS means if you understand one MOSFET, remaining PMOSFET are working is same only, just vice versa. So that means in enhancement MOSFET you are giving positive gate voltage, in enhancement PMOS you are giving a negative gate voltage. Here in channel is forming due to electrons, here channel is forming due to holes. Okay, and the drain current also you are giving here positive in enhancement. In the PMOSFET you are giving negative. Okay, so normally you are getting the characteristics for enhancement MOSFET in first quadrant, but here both are negative, you are getting at the third quadrant. Okay, that we'll discuss in the next session. Okay.